Okay, so we need to get back to the noise analysis of the LNA. So what I will do, so remember that you have this the cascode LNA. Okay, and this is your output. So what we want to find out is the output short circuit noise current. Okay, so let us assume that we are finding out. Did we do the output short circuit noise voltage or current? If we do the voltage, let's do the current because it's easier. Okay, we can also do the voltage, but basically what I'm going to assume the cascode does not produce any noise, which we already assume. I want to find out this current. If there is a short circuit noise here, this would be ISCN, right? So basically I'm going to assume RDS is very large, much larger than other impedances. Whatever current flows up into the cascode flows up. If you're doing open circuit voltage, it gets multiplied by RD. Okay, to produce the voltage. If you're finding out the short circuit current, it produces a short circuit current equivalent to this current flowing out, right? So if I were to draw the small signal equivalent circuit for the noise current, okay, it would look like this. So, sorry, I have the resistance RS, inductance LG, CGS. So this is GM VGS, where this is VGS. I also have noise of M1, IN1, and effectively I am trying to find out ISCN. Okay. We can keep the other direction, it doesn't matter, right? And here we have LS, right? So this is the equivalent circuit. So I guess we came up with various expressions in class. I tried to find out the easiest possible way to get this, right? So what we'll do, we'll try to write down some KVL, KCL expressions and try to massage them such that we get into the simplest possible way. So first question, what is the current through LS? What is the current through LS? The current through LS is equal to the current through CGS plus ISCN, right? So the short circuit noise current splits in some way as GM, VGS and IN1 and then recombines back at the other node and then eventually adds with the current through CGS to flow through LS, right? That is if you were to apply KCL at this node. Is that okay? So if you were to look at this voltage VLS, what is the current through CGS? So S CGS into VGS, right? Plus, in this case, it's minus ISCN. Because of the direction, we have taken the direction outwards. We have taken the current, short circuit current flowing out into the short circuit. So the reverse current is minus ISCN. Sum of those two will be flowing through LS. Okay. So this times SLS. Agreed? Okay. And of course, you know that ISCN plus remember that this is noise Of course, ISCN is going to be correlated to IN1, GM-VGS is going to be correlated to IN1, etc. Because the only source of voltage or current in the circuit is the noise. So everything is correlated. You have to run with amplitudes and not squares. Right? Okay. So ELS, if you were to write this, would be S squared LS CGS times VGS. So this is what this would give you, SLS times this is okay. Okay, and now I can write KVL around this loop. Okay, around this loop. So 0 is equal to S CGS VGS is the current flowing through the first part of that loop. Into what do you have there? RS plus SLG plus 1 over S CGS plus of course VLS. Is this okay so far? Okay, so let us see what we want. We finally want ISC. So actually instead of rewriting this way, it is probably better for us to write VGS in terms of ISCN and IN1. Right, so we should have written it in a different way. So VGS is is basically minus of ISCN plus IN1 by GM. Right, that might have been better. We did not, maybe we didn't need this. Let's figure out whether we need this or not. So 0 is what was the VLS? Let's write this down. I think we will need it. S square LS CGS VGS plus SLS into GM VGS Is this right? Okay. So let's combine the VGS terms. So VGS into what do we have? So S square CGS into LS plus LG. So you have three terms so far. These two terms gives you S square CGS LG into VGS. This term gives you this. So if you combine those two, it gives you S square CGS into LS plus LG. These two terms gives you just VGS itself. Okay. So plus 1 plus S CGS VGS into RS plus SLS into GM. Sorry. Is this okay? Have I missed any terms? Everybody's following this? Okay, I hope I have not missed any terms. If I have made any silly mistake, just tell me. So what do you know about this at the resonant frequency? If you were to set S equals j omega naught, right? S squared CGS and LS plus LG plus 1 will go to 0. Okay? So which means VGS is basically minus SLS into IN1 by SLS plus SCGS RS. So let me see if we can write this even better. IN1 by it's okay. We'll just leave it like this. We'll just write it down as minus LS. We can do any operations later. Is this okay? Have I made any mistakes? SLS GM, that's what I thought. Okay. Because the dimensions were not working out correctly. SLS into GM. Yes. Is okay? So in fact now, so minus LS by GM LS plus CGS RS. Okay, we'll leave it like this. So now I can go back to this equation. Remember that VGS is also minus of 1 over GM times ISCN plus IN1. Okay. So LS times IN1 by GM LS plus CGS RS is equal to ISCN by GM plus N1 by GM. So ISCN This is okay? So minus let me divide the numerator and denominator by CGSRS 1 plus GMLS by CGSRS times IN1. Remember that we have set omega t times LS is equal to RS. This is what we have set earlier. GM, we said that omega t is approximately GM by CGS. So which means GMLS by CGSRS is equal to 1. Make sense? So which means ISCN is minus IN by 2. Is okay? Half the current from the transistor flows through the output. Any mistakes in the equations I have done? This seems to be the simplest way I could find. Right? Have I made any mistakes? Anyway, go over it once you get back. Right? Okay, instead of splitting the two currents, this seems easier. This is independent of frequency. Having said that, it is independent of frequency assuming that you are operating at resonance. Okay, what that means is, if you would like to design a 900 MHz LNA or a 2 GHz LNA or a 5 GHz LNA or a 10 GHz LNA and so on, around your band of interest, half the noise current will go to the output. Does that make sense? Okay, irrespective of what the center frequency of operation is, half the noise from the transistor will go through to the output. That's what this means. Okay? Lowest value of noise may not be the operating. What does that mean? What does the lowest point of noise figure mean? Okay, since you are saying all of this because you seem to have already simulated some LNA structure, we have not even seen what noise figure is. Your question is extremely premature. Okay, so let us wait till we get to the expression for noise figure, then maybe you can ask a question. We have not even derived noise figure yet. Right? I understand what your question is, but maybe the other people do not know what you are talking about. Right? So maybe we'll come to the noise figure and then we'll come to your question. Okay? But more importantly, this is the correlated noise flowing through the output. Right? What is ISC n squared? Is actually IN squared by 4. What is this? So this is 1/4 of 4 kT gamma delta F. So this is basically 4K. It is just kT gamma GM delta F. Is it okay? Okay. Of course, we did not, to do all of this, we did not have to use the short circuit noise at all. Right? If this current, all this current will flow through the cascade, flow through the output, get multiplied by RD, etc. Right? You can also do it that way, it doesn't matter. Okay? So the noise, squared noise current is kTgm delta F from the transistor M1 into the short circuit. What is the noise from RD? Is equal to 4 kT by RD delta F. This is the noise from the resistor. We now need to divide all of this by the large signal transconductance. Right? How do we obtain the large signal transconductance? Or not the large signal transconductance, the transconductance. Right? Earlier we established the transconductance in terms of Qin, etc. Right? Now what we'll do, we actually have that expression here, because what we can do, instead of IN, imagine that you had a voltage Vin and you did not have IN1. You can write the same KVL just for signal alone. So let us quickly do that. So now I want to calculate, so GM of the LNA. Okay. So to do that, we will draw the small signal equivalent circuit also, except we'll now add Vs we won't have IN1. Right? We'll only have VGS. So this is CGS, LG, LS. Of course, GM is basically ISC by PS. This is what we want to find out. How do you find this out? Exact same thing. What is the voltage across VLS? Right? Earlier you did KVL around the loop. We'll do the same thing, except now instead of 0 on the left hand side, you'll have Vs is equal to SCGS VGS into RS plus SLG plus 1 over SCGS plus VLS. Can you please do that now? In the next 2 minutes, I'll also do it. Why don't you folks also do it? Right? Sorry? Yeah, so I'm trying to write it in a better way. So what I will do, I'll by 1 plus okay. So this is basically so this portion is 2. This portion is 2. So if I were to write it, I would write it as 1 by 2 Rs. So I'll write it as Gm of omega naught now. Okay. Magnitude of Gm of omega naught. We are interested in the magnitude of the transconductance. What is this? What is Gm by Cgs? Omega t. Does this make sense? So this portion is equal to omega t. So the magnitude of the transconductance is basically related to omega t over omega naught. Omega naught is of course the frequency at which you are operating. Okay, where you applied omega naught square CGS, okay, into Lg plus Ls plus 1 is equal to 0. Right? What is the condition for omega naught? Omega naught squared CGS into Ls plus Lg plus 1. This is the condition. Rather, minus omega naught square. Right? Because you had a j omega whole square. So, this is the operating frequency. At this frequency, okay, you can see that the effective transconductance of the device is actually independent again of a lot of things. It's independent of device parameters almost, except for omega t. Okay, it is not dependent on other parameters. It is not dependent on Ls and Lg directly at all, except for the fact that product of omega t and Ls has to be Rs. Right? Everything is kind of captured here. It assumes a lot of assumptions. Okay, but what this tells you is if you were to keep omega t constant, how do you do that? By scaling the device and the current together. That is how you keep omega t constant. Right? If you were to do that, you can see that the effective overall transconductance of the device stays the same. Okay? Remember earlier we wrote it in terms of Q in etc. Okay? So Q in itself is a function of the operating frequency that had some frequency dependence in between inside. Why is that? At that particular frequency, if you write it in terms of Q in was actually omega naught into Lg plus Ls over 2Rs. There was some inbuilt dependence on omega naught. We didn't see it. It looked like the voltage gain was constant. But actually the quality factor changes depending on what frequency you design at. Does that make sense? Whereas this one shows you a slightly different dependence on omega naught and omega t. Okay? Sorry. Okay. Any questions? So now all we have to do is take those two noise sources, divide it by the GM and apply noise figure equation at the input directly. Right? That's a lot easier. So, and the noise figure expression is basically 1 plus VNN squared over GNRS squared. Can you please write this and tell me what answer you get? Is this correct? Sorry. Okay, is 1 over gm squared. So it's 4r squared into omega naught by omega t the whole square. So 1 plus, so gm1 rs 4 kt goes away, omega naught by omega t squared plus 4 rs by rd into is this okay? Have I got this correct? Is this what you folks have got also for the noise figure? Okay. So, first things first, right? How small can this be? That is the first question, right? Then we'll come back to why the minimum occurs at a different, is different and so on. So first question, how small can this be? Suppose I get rid of, so the second term, right, as you can see, it's a function of both omega naught, omega t and rs, ratio of rs to rd. As rd increases, right, the output tank becomes more and more ideal. If if you had an ideal tank, it would not produce any noise, right, related to rs, right. So, but really, in a real LNA, you can only get RDs of the order of 200 ohms, not much better. Okay, but what this is telling you is to maximize RD, which means maximize the value of Q as well as of the output tank, as well as maximize the value of LD probably, if that is limiting your Q. Okay, okay. How small can this be? Well, why don't you work out some numbers? So let us say omega naught by omega t, now you need to assume something. So let us say it's about maybe a fifth or so, 1/5. Okay, you can take a number. So about 0.2. So let us say gamma was about 2, worst case, right? Gamma of 0.67 for long channel MOSFETs, and I told you it can be larger. So let's take the worst case. Gamma is equal to 2. Okay. What else we need to? RS is 50 ohms, of course. Let us say RD was some 200 ohms. Only 4 times that. That is quite rare, right? I mean, no, that's not quite rare. That's quite common. 200 to 400 ohms is probably what you can achieve. Okay, unless you have something special in the process going on. So first of all, the final parameter left is GM. Okay, what do you assume for GM? And how does it affect your circuit? Does it affect the overall transconductance? Actually, it does not. The minute you set omega naught and omega t, okay, the value of GM itself can be set to almost anything. The transconductance and gain of the circuit does not depend on GM. Okay. The transconductance is 1 over 2 Rs times omega t by omega naught. If omega t by omega naught is 5, right, you can see that the overall transconductance is about 50 millisiemens. If omega t by omega naught was 5, right, this is about 5 by 100, right, which is 50 by 1000, which is about 50 millisiemens, right, capital GM. So 5 by 2 RS, which is 5 by 100, is about 50 millisiemens. Okay. Small gm does not figure except in the omega t itself. You can choose, there's a wide range of gms for which you can achieve the same omega t, of course. Okay. So if you were to choose, let us say, you can now pick a gm and see what kind of noise figure it will give. The larger the small gm you pick, okay, the larger of course will be the noise figure, right? You can pick some large number, let us say 100 millisiemens. Let us say for the given current consumption spec, right, omega t is achieved, with the current consumption at 100 millisiemens, let us say. What would be the noise figure? So 0.1 into 50, that is 5. So let me maybe write this down. Into 2. What does this give you? Is this right? 1.44? What is noise figure? This works out about 1.6 dB. As you can see, sub 3 dB very easily achievable, right? Sub 2 dB also very straightforward. If omega t was larger, right? What do I mean by larger omega t's? For a given GM, you have a smaller capacitance for the device, which means as the process scales, which happens automatically for you, right? As the process scales, the effect maximum FT that you can achieve with the process only increases. Okay? For a given current consumption, for a given GM, you can get even better omega t's in faster processes. It tells you that the noise figure will keep getting lower, assuming that gamma was not scaling, right? So as you can see, by and large, this would be the most popular LNA for systems that are noise figure limited, for narrowband systems that are noise figure limited. What is the disadvantage of this? Narrowband. Okay. Now, just remember that this particular LNA gives you very good noise figure because of what? Why does it give you very good noise figure? I mentioned this in passing. Noiseless input match. Okay. Anything else? Apart from noiseless input match, after you have done noiseless input match, you are getting passive gain through the input matching network. I mentioned that once. You get a gain of Q in, right? So if your Qn keeps increasing, which happens at higher and higher frequencies, right, at very high frequencies, what will happen is that the effective noise figure that you can still achieve, as long as you are far away from omega t, can be really, really good compared to, for example, the common gate or the resistively matched input, where you have the shunt resistance at input, right? Because of the passive gain from the input match. How do you increase that passive gain? How do you get even better noise figure? I want to push up, push down the noise figure. How do I do it? I need a higher quality factor. If I build a higher quality factor, RS, the resistance portion is 2 RS, that's fixed. Okay, omega naught is fixed. How do you improve? Omega T times LS is RS, right? How do you, so you have the, remember the only thing you have to play around with is CGS. Remember that, because the Q is 1 over 2 RS CGS. Forget about LS and LG. So you have to cut down CGS, okay, that will increase the Q of the input match. Automatically, if you do that, if you cut down CGS, you can do it in 2 ways. One way to do it is to cut down CGS and keep omega T constant. If you were to do that, the value of LS will remain constant, the value of LG will increase. Does that make sense? I can cut CGS but decrease current also such that omega T stays constant. I only have CGS scaling. If CGS scales, LG has to increase. So let me put that down in letters. So I want to increase Qin. Needs to increase. CGS needs to decrease. LS is of course constant, which means LG will increase. So you will get larger and larger LG, same LS, smaller and smaller transistors for smaller and smaller CGS. Does this make sense? Because LS plus LG has to resonate with CGS. Okay? Okay, so maybe we'll stop here. In the next class we'll see how you, so question is how far can you push omega T itself? That also we'll see in the next class. What happens if you try to over design on omega T? Okay? We'll take some typical numbers and see what happens to LS, etc. Okay? We'll stop here.